Now we turn verifiable credentials into a real backend capability. An issuer service accepts a request, checks the subject, builds and signs the credential, and records what happened, so issuance is secure, traceable, and ready for production applications. At this point, you have the building blocks: identity models, VCs, DIDs, cryptographic proofs, schemas, and credential formats. The next step is to connect those concepts inside a working issuer service, the first backend component in our VC architecture. Think of the issuer as a digital registrar. It decides whether the subject is eligible based on evidence, policy, or business rules. Then it turns approved claims, such as identity, certification, or membership, into a credential payload. The critical step is signing. That signature lets anyone later detect changes and confirm who issued the credential. After delivery, the holder controls presentation. So strong systems keep approval logic separate from the cryptographic issuing service. The issuer backend works best as a controlled pipeline. Requests enter through an API layer that authenticates callers and validates data. Identity and eligibility checks determine whether issuance is allowed. The credential builder translates business records into a standards-compliant verifiable credential. Signing happens behind a stronger boundary, such as an HSM or KMS, so issuer keys stay protected. Finally, storage and audit logging preserve evidence, status, and revocation references for operations and compliance. Before issuing anything, define the credential types your service will support, and bind each one to a validation model using JSON schema or JSON-LD contexts. A degree, employee badge, and membership credential may share infrastructure, but their required claims, eligibility rules, expiry policies, and schemas can differ. Treat these definitions as public contracts, not database tables. Version them carefully so verifiers can keep trusting older credentials while you evolve claim structures over time. The first approval question is simple. Who is this credential really about? A login proves control of an account, not necessarily entitlement to the credential. Subject identification should rely on trusted evidence, such as institutional records, verified documents, prior credentials, or an identity provider. Then the service can match the request against authoritative data, confirm eligibility, and resolve messy cases like duplicate accounts, name changes, stale records, or account recovery before approving issuance. Once the subject is identified, the issuer still has to check which identifier the credential will be bound to. If the credential subject.id is a DID, the requester must prove control of that DID, usually through DID authentication, a signed challenge, wallet-mediated proof, or prior account linking. Without that step, an attacker could ask for Jane's credential, but insert their own DID. Binding creates the secure link between the holder, their key, and the issued credential. A practical issuance API separates the request lifecycle from the signing step. A user creates a credential request, receives a stable request ID, and can check status as it moves through pending, approved, issued, rejected, or failed. In approval-based flows, admins review the request before calling the internal issue endpoint. After signing, delivery can be direct, wallet-based, or handled through a short-lived secure link. Keep responses predictable with clear status values and error codes. Treat issuance as a controlled workflow, not a one-step database insert. A request should identify the credential type, the subject, and the evidence being claimed. The service then validates schema, rules, authentication, and eligibility. Low-risk requests can move to automatic approval, while suspicious or high-impact requests go to review. Only after approval should the system build, sign, and deliver the credential. Modeling each state also supports retries, monitoring, fraud handling, and later revocation. The credential builder is the boundary between private business data and public claims. It does more than copy fields. It applies the VC schema, sets context, type, issuer, subject, issuance, and expiration dates, and validates the unsigned payload before signing. Just as important, it decides what not to include. Internal IDs, workflow notes, or sensitive attributes should stay out unless they are intentionally part of the credential design. Deterministic construction also makes tests and audits repeatable. Signing is where an unsigned credential becomes trustworthy. The signing module applies a cryptographic proof, such as a JWT-based VC, data integrity proof, or linked data proof, according to the ecosystem you support. Treat this as a hard trust boundary. Private keys should stay isolated in a KMS, HSM, enclave, or signing service. Every proof must reference the correct key identifier, and the design must support rotation, compromise response, and verification of older credentials. Issuance APIs need the same level of protection as payment or account recovery systems, because one successful attack can create real fraudulent credentials. Start with strong authentication for every caller: subjects, admins, services, and wallet clients. Then authorize each action against the specific credential type. Add abuse controls such as rate limits, replay protection, idempotency keys, and strict request validation. Log security events for investigation, but avoid collecting personal data you do not need. Once a credential is signed, delivery is a security decision, not just a transport detail. A direct API response is fast and simple, but the application must protect storage and keys. Wallet delivery shifts control to the holder and supports later presentations. QR codes and credential offers are useful for cross-device or asynchronous flows, but links must be short-lived and bound to the right user. Design delivery around what the holder needs to do next. After issuance, the issuer still has retention choices to make. Keeping the full credential can make support, recovery, and reissuance easier, but it also concentrates sensitive data and increases breach impact. Storing only hashes or metadata lowers privacy risk while preserving evidence that something was issued. Separate status records enable revocation, suspension, compliance checks, and investigations. Aim for minimal retention with strong audit logs, tamper-evident, access-controlled, and free of unnecessary personal data. You now have the issuer blueprint. Accept a request, validate the subject, bind the DID, build and sign the credential, then deliver, store, and audit responsibly. Trust depends on protected keys, careful privacy choices, and clear evidence. Next, we follow credentials into wallets, presentations, and verifier decisions.